I'd like to tell you a little bit about the Science Gateways Community Institute. We are funded by the National Science Foundation to provide services, and we provide them those services and resources in three main areas. The first main area is support for building and running gateways, and we do that in several different ways. One is by providing hands-on development support. We also have other consultants who can provide advice about areas very specific to gateways, such as sustainability or cybersecurity. And then we also provide a catalog of gateways and software to make gateways where if you have a gateway, you can list it there, or if you're looking for inspiration or tools, you can look there for existing examples. And then we also offer a variety of education and training, including this webinar series. We have right this minute going on is the Gateway Focus Week in Chicago. This is offered twice a year, and it's an intensive week for you and your project teammates to focus on the work that you're doing with your gateway and think about everything from stakeholders to the marketing opportunities to sustainability and so forth. We offer a variety of student-focused programs, mostly during the summer, but also during conferences. And we have our annual conference, which is in 2 weeks. Finally, we have a number of website resources and materials you might want to look into. And then finally, as our name suggests, we're all about community, and we offer a number of different ways for you to network and connect with our community, which includes a partner program of various partners who offer complementary services and opportunities and communities that you might want to know about. We have an affiliates program for those who have software that you would like to promote on the catalog and are willing to support if someone contacts you through finding out about your software from our catalog. We, of course, welcome information to add to our news and job postings. We also take guest blog posts. So if you'd like to talk about an experience that you think would be valuable to the community, let us know. We also have a community forum on Google Groups, which the very first slide mentioned, but you can go to our website and join that, and it's an opportunity to connect directly with other people who have similar experiences and background, and as well as different background, to ask for their input about things you might be struggling with. And of course, our conferences and networking opportunities. So these areas are all interacting, particularly through there's five general areas that support these three different main areas of activity, and you can find out about all of them on our website, sciencegateways.org. And so before I hand off to our presenter, I just want to make one brief plea that if you enjoyed this, or even if you didn't, but please share your feedback about this webinar so we can tell NSF that we're doing something with their funding to support this community. It doesn't take very long. In fact, it probably takes less than 30 seconds to let us know how you liked it. And I'll post this link in the chat area just to make it easier for you to go and give feedback. It also includes an open text area for you to suggest additional topics. And we do take those seriously and look at them, and that shapes some of what we have offered during our webinar series. So with that, I'm going to stop sharing my screen and hand this off to Joe, who is from the Texas Advanced Computing Center. He is a research associate and lead of the Cloud and Interactive Computing Group. Joe Stubbs is, I think, as I understand it, very closely connected with Abaco and behind a lot of its development. So he's going to tell you everything you wanted to know about that, for at least for now. So with that, I'll hand it off to you, Joe. Go ahead and you can share your screen as soon as you're ready.
Awesome. Thanks, Catherine. Yeah, so I have the screen shared.
Yeah, I can
everybody
see
it okay and hear me okay?
Yeah, I can hear you too. Yeah, fantastic.
Okay, awesome. Well, yeah, let's go ahead and get started. Yeah, so my name is Joe Stubbs, and the title of my webinar is Portable Scalable Computation with Containers and Abaco Functions. So I just thought I'd kind of set the stage a little bit with a little bit of background about me. So yeah, so my educational background, formal training is in mathematics and theoretical computer science pretty much, but I have been a research associate at TAC for about the last 6.5 years or so. And we formed the Cloud and Interactive Computing Group, CIC, in March of 2017. So that's kind of been my focus since then. I lead that group. It started as 3 people, but we've really, seen tremendous growth over the last couple of years. And today we are 15 full-time staff, plus undergraduate students who do research projects and professional interns. So we focus on cloud computing systems for research computing, APIs, and other kinds of systems like Jupyter. And our work is primarily funded by the NSF, the National Science Foundation, but increasingly we've been working with other agencies like DARPA, the CDC, and even the NIH. So just to give an overview of the webinar, what we're going to be talking about today, I thought we would start by just kind of setting the stage with a sort of motivating example. And I'm going to talk about this image classifier program that we have that's written in Python. And the idea is, we've got this program, it's a research code, it happens in our case to be an image classifier, but could really be anything. And we're going to kind of talk ultimately about how we could run that code on our Abaco cloud. So to do that, to get there, we're going to do a crash course introduction to containers in Docker. It's by no means going to be a complete or exhaustive treatment, but we're just going to kind of give a quick overview. And then we're going to kind of talk at a high level about serverless computing or the so-called functions as a service model, and then go into Abaco and talk about some basics of the Abaco platform. We're not going to be able to do an exhaustive treatment of that either, but I'll give some pointers to some documentation and other resources for learning more about that. And then finally, we just thought we'd end by walking through this example of how to take our classifier program and run it on Abaco. So with that, I'll just go ahead and jump right in. So yeah, so setting the stage. So suppose we have this classifier program. Happens to be Python. That's just the language that I like, but it could be anything, right? It utilizes Python itself, of course. This TensorFlow package, which is a machine learning, kind of library, and it also utilizes requests, which is a Python package for making HTTP requests. And it's used essentially like this, right? Python, classify image.py, that's our script, and then -- image file, some URL to an image. And, so if I were to do this and say, Python, classify image.py, -- image files, this bit.ly URL here, and if that bit.ly URL happened to point to a picture of this cute doggy, then what would happen is my classifier program would download that file and run this pre-trained classifier on it. And it would print out some log messages, but essentially you would see at the end this score, the scores of the different classifiers or classifications that the classifier tried. And so you can see that Labrador Retriever came up at the top at 97%. So it basically classified that as a Labrador Retriever. So cool, right? I mean, that's cool. That's a cool program and useful. And it's kind of an exemplar of what we see a lot, right, in research codes. And so the idea is like, I've got this thing, I can run it on my laptop. That's cool. But what if I want to, share it with other colleagues or other researchers or, embed it in a science gateway, or maybe even just scale it so that I'm classifying tens of thousands of images. So we're going to kind of try to tackle that here. So like I say, just a brief crash course overview of Dockers, of containers and Docker in particular. Containers, basically the takeaway for this, what you need to know is that they are reproducible application environments, right? At their heart, containers are a mechanism for isolating programs, or operating system processes from other programs running on a machine. By the way, I wanted to point out that if you haven't, be sure to check out this SGCI webinar that came, I think, in July. Bob Killen and Jeffrey Sika, hopefully I'm saying that right, Containers and Kubernetes. It's great. They do a much more exhaustive treatment So just a plug for that. But yeah, at their heart, they are these isolated userland programs. And in particular, they contain all the files that the application or the operating system process is going to need to use. And so that makes them portable. And so containers are going to be one of the key ingredients for our solution for porting and scaling our Python program. So Docker really is a platform for containers. People think of it as the runtime, and that's true. There is the Docker runtime, but it also has the images, the notion of a Docker image and an image builder system based on Docker files, which we'll actually talk about a little bit because we need Docker files and images. And it also has the Docker Hub, which is a HTTP-based registry for images. It's a place where you can share images that you've built, and you can download images created by the community. So we'll be talking about Dockerfile and Docker Hub a little bit in more detail, but just know that the Docker is one container platform and one runtime of many. And it wasn't the first, and it certainly won't be the last. But it is the container runtime that we're going to be using with Abaco. So I do, like I say, want to talk a little bit about a Dockerfile because it's how we build images that we can use to port our applications to other systems, other computers that have Docker installed. So overview of a Dockerfile, it's just a text file with instructions for how to build a Docker image where our application can run. You can basically think of it as a recipe for how to add files to a rooted file system, right? It initially starts out empty. There are no files in it, but through a series of commands, we add files to it. There's a set of reserved words. We're not going to go over all the words, but from, run, add, CMD. We're going to go over a couple of these basics. And this is how we're going to put together a Docker image for our classifier. So on the left here, we actually have an example of what would be, a realistic example of how we might package our classifier. So we start with the from instruction. And what this does is it basically says we don't want to start from a completely empty image. We want to start from a known image, presumably something on the Docker Hub or something that I've built locally on my machine. So here we're saying from Tensorflow and then some particular version of Tensorflow in Python 3. So this from instruction says grab all the files that were already put into that image and start my image with those. Okay, and now the run instruction allows us to run arbitrary commands, CLI commands in our image to add or remove or modify files. So here we're running the standard pip install command. This is going to be familiar to people who are familiar with Python. This is the standard way, or a standard way anyway, of installing Python packages. So here we're pip installing requests. You might recall that requests was a library requirement of our classify image program. So that's what that does. And then here we're using the add instruction to add local files from the computer where we're going to actually build this image to our image. And you can see here we've got a reference to classify image.py. That's the actual script we wrote. And we're saying add that to / classify image.py in the container image. That would copy the file from the local machine into the image at that path. And finally, command, CMD, the command instruction adds a default command to run as the program that's going to run inside containers launched from this image. It takes a particular format, which is a list or an array of instruction and then followed by arguments. So here we're running Python 3 and passing classify image.py as our command. So this is a working example actually of a Dockerfile that we might write for our classify image program, even if we weren't thinking whatsoever about Abaco or functions as a service. Okay, and so once we had that Dockerfile written, we could run a statement like this here at the bottom, docker build, to build the image. The -T flag here just specifies a label for the resulting image built. So here I'm using JStubbs as my namespace on Docker Hub, and then SGCI classifier. And the dot here at the very end says, to Docker build, it says, use the current working directory as the working directory for the build. So in other words, like when it sees things like add this classify image.py, it's gonna look in the current working directory for those kinds of things. So assuming this build succeeds, and it should if we have a classify image.py file locally, etc., then at the end of this build, we will have an image JStubbs SGCI classifier that has our TensorFlow program in it. Okay, and once we have that, we can run containers from that image. We can run one or more containers from it, and we just use this Docker run statement. The simplest form is Docker run the image to run. But we can pass additional options to do things like mount additional directories from the host or expose ports. We can also pass a different command to our Docker run and so forth. So that's how we run containers from an image. So there's a lot of confusion at the beginning about images versus containers. The point is that an image is basically a container template, right? It is the file system together with the metadata that says this is how containers should be run. But you can run many containers from the same image, and they all get, if you will, a sort of isolated copy of that file system. So in other words, if I run 3 containers, and the first one changes some files on the image, the other 2 don't see any of those changes. So that's the crash course on Docker. Hopefully that catches everyone up to speed. And so we're going to switch gears and talk about functions as a service, also sometimes referred to as serverless computing. And it's basically a cloud computing model and a software architecture for building applications on the cloud. And it does have roots in projects like PyCloud that started around 2010 or 2011, but most people think of it as originating with the sort of, still to this day, most famous and well-known commercial offering, AWS Lambda. And I think that started in 2014. So it's a fairly new model, the last 5 years or so. And basically the way that it works is that you, the user, or application developer, register a small program with the cloud computing offering. You can think of this as like a little function or a program that's going to ultimately run on the cloud. So you register it, and that's a sort of one-time step. And then you invoke that function through a series of API calls, one or more API calls. And the cloud provider, in response to you sending these API requests to invoke the function, actually runs the function somewhere. It runs it somewhere on its computing infrastructure. Now, where it runs, you, the user, the application developer, don't know. And the idea is that you don't care, right? The whole point, or a big point of this, is that you don't have to worry about servers. And that's where it gets this moniker, serverless computing. Certainly there are still servers, right? AWS still is running servers, and Abaco, we have servers, but you, the application developer, don't know and don't care about those servers. You just know that somewhere your function is getting run. So I definitely don't want to paint too rosy of a picture here. There are definitely pros and cons to this model. I think on the one hand, it does encourage modularity. You have to think about the ways in which you can package up your application capabilities and functionality into these individual little components that can be registered. And with modularity comes a lot of other benefits, such as being able to scale the components individually, right? So that if one component is getting a lot of traffic, we can give it more resources, either put more copies on different servers, if it can be scaled in parallel, or put it on a bigger server with more resources. But we get that independent scalability. And we get an automated scalability, right? I mean, this is, like I say, the kind of the big the big win for a lot of people is I don't know or care where it's running. Someone else is managing that for me. But I do think there are some downsides to the architecture, right? Probably the biggest one is the difficulty in predicting performance. Because you don't know what those servers are or how big they are, or even what other users are running on them, it can be really hard to predict performance of your application. So there are certain types of apps and certain types of use cases, basically ones where the performance can vary that are better fits. And I think it also is true that it can be harder to reason about applications developed this way. Essentially, when you break down your application into a bunch of tiny little components, you end up moving a lot of complexity into the communication that happens between those components. And a lot of tooling and other things aren't necessarily equipped for reasoning about those, and so that it can make it harder to reason or debug those kinds of architectures. So today, FaaS is a really pretty popular thing. There are lots of both commercial and open source offerings. All the major commercial cloud providers have them. AWS Lambda, Google Cloud Functions, Azure has Azure Functions, and then there are open source projects as well, like OpenFaaS and Iron Functions. Today we're going to be talking about Abaco. It is certainly an open source project, and it is, I think, to a sense, a functions as a service platform, but it has a little bit different focus from all of these, and so hopefully, we'll kind of at least get some of the hints of how it might differ. So the idea with Abaco is to combine Docker images and Docker containers with something called the actor model of concurrent computation, which we'll talk about here in just a second, to basically provide a functional computing platform. It is serverless in the sense that users only ever interact with that API, and they don't know where their actors are running, but it focuses on research computing use cases instead of enterprise services. So I'll hopefully kind of get that across in some level. We have these kind of three primary capabilities that are layered on top of the actor model. We think this actor model is a rich sort of programming model for a number of sort of higher level use cases. Unfortunately, I'm not going to have a lot of time to go into depth on those things, but just know that they are there, and there's more about them in our documentation. And I should say that this is work supported by the U.S. National Science Foundations. So what is this actor model? So in the actor model of concurrent computation, this is a theoretical model dating back to like the 1970s, where the fundamental computational primitive is something called an actor. Okay, and an actor is a single-threaded thing. It's a single-threaded computational primitive that essentially does all its work in response to messages it receives. So the fundamental idea is that an actor is going to receive a message, and in response to that message, it's going to have three things that it can do. It can do some local computation, do some local logic, and save the state, save the result. It can send a message to other actors for which it knows the address of the actors, or it can create new actors. And that's it. That's all it can do. And so it's a very simple model of computing, but it turns out to be a quite powerful one. And in particular, it kind of makes it easy to reason about concurrency. So this is an inherently concurrent model. There's no ordering put on the way that messages are computed from different actors. And in practice, as an actor model system evolves, more and more actors are created. And so there's this idea, this inherent concurrency that actors are just messaging each other and computing things, and so you don't have to layer a separate notion like threads on top of this to get concurrency. So with Abaco, the idea is to provide user-defined actors. And the way we do that is we say that a user can associate an actor with a Docker image. They basically register an actor by providing a Docker image or a reference to a Docker image. And then the Abaco system assigns that actor a URI, an HTTP URI, which is the actor's inbox or mailbox, which is the place where messages can be sent to. And so you send messages by making HTTP requests to the actor's inbox. And in response to those messages being sent, the Abaco system will launch a container from the associated image and inject the message data into that container. So this is just a sort of pictorial view of that. We start with an image, we post that to the Abaco actors collection to say, we want to create a new actor associated with this image. Abaco responds with a URI to the actor, and that's sort of the permanent kind of set in stone URI for our actor. And now we post to the messages endpoint underneath that actor ID some message data, and in response to that, Abaco will launch a container, depicted here A, injecting the message into that container. And so how does it inject that message? Well, it actually depends on the content type of the message. So we can handle things like binary data, JSON data, but basically for text data, Abaco is going to create an environment variable, MSG, in the container that has the string value that was the message. So that's the basic mechanism, and that's something we're going to need to keep in mind when we go to making our classifier program run on Abaco. We need to be able to handle this message environment variable that's going to have the data of the message. Okay, so how does Abaco compare to some of those other platforms? It's an open source project funded by the National Science Foundation, and it's hosted here at TAC. It's free to use for researchers. And so for a lot of people, like that is the main kind of differentiator. If you go to AWS Lambda or one of the other ones, you do have to find a way to pay for that, or get somebody to pay for that. And this is hosted by TAC and funded by the NSF. So you're just able to use this for free, up to a certain level. I mean, we have basically an amount of computing that's available for free for everyone to use. We do have people who essentially buy into additional hardware so that they can have dedicated Abaco hardware, but that's not a requirement. But it also leverages this actor model that I've been discussing, and so there are a lot of other aspects to that. We have things like state that can be stored, aliases, links, attributes of the actors that can kind of enable you to build larger networks of more complex things, which we feel is an advantage, at least in the research computing use case. But that's a difference. And we do other things, like we allow executions to run much longer than most of the commercial clouds. Like, AWS Lambda, I think, at least the last time I looked, it had about a 5-minute execution limit. You're able to run for hours on a single actor execution. And you can also have access to more CPU cores and memory and even specialized hardware like GPUs than I think is available in the commercial cloud. It also integrates with other TAC resources. So we can give you POSIX interfaces, directly in the actor containers to our high-performance storage systems like Corral and Stockyard, our global work file system. And we do pre-authentication so that you can do other API calls from within the container, and it integrates with other environments like our Jupyter environment. It can also be installed and run at other institutions. So you can take Abaco, run it on-prem, and sort of have a dedicated computing capacity there. So this was a NSF-funded project. The funding started in 2017, I think September 1st of 2017, and so we had kind of our initial release in January of 2018, external release. So since that time, we've had about 40,000 actors registered, 600,000 executions, 7 million seconds of runtime. You can see 1.3 times 10 to the 18 jiffies of CPU utilized, right? So I mean, it's nothing obviously compared to AWS Lambda, but definitely getting some sizable usage in the community, and we're partnered with a number of large and small cyber infrastructure projects, Design Safe, Cybers, the Synergistic Discovery and Design Environment, GenApp, and we're partnering with the CDC to get components of Abaco installed on-prem there.
Hey, Joe, a question
Yes.
has popped up.
Sure.
Sean asks two questions. What other institutions host their own API instance, and what happens when funding dries up? I don't know if he means your funding or their funding.
Right. Great questions. Okay, so Abaco is currently just at TAC right now. We have the CDC that has basically a pre-production environment install of that, and we're currently working with them just through some DevOps issues that they're facing. If this is Sean at the University of Hawaii, then he may know that Sean. We're also. Oh, okay, cool. then yeah. So there's another Sean who is also looking to potentially install this at the University of Hawaii. So we have a broader API platform we're calling Tapis here at TAC that has a bunch of other APIs in it essentially, and those are on site at UH and CDC and a couple of other places. And so this one being a newer one that is still not in any of those places in a production environment yet, but I think we'll probably have those by the end of the year, this year, if not soon thereafter that. What happens after the funding dries up is a good question. So Abaco itself is only funded through the end of 2020, but it is part of this larger Tapis project, which is just started actually. So Tapis has been around for a while, but we've kind of rebranded it to Tapis, and we're adding some new capabilities. So we have a 5-year grant from the NSF that just started actually September of 2019, to which Abaco will be a part of. So for the next 5 years, Abaco has very solid funding from itself and then from these external things. But we also have funding from various projects that keep these things going. And so in terms of our funding trajectory, I think it's very hard to predict in these things beyond much more than about 5 years. But we don't have any reason to be concerned now, I guess is the way I would.
Okay. Yep. That's it for now.
Cool. All right. So I will turn now to taking that image classifier program that we started with at the beginning of the webinar and seeing what would it take to run this thing on the Abaco cloud. So we're assuming we have this script, right? Python classify image.py -- image file equals something. And we're going to put it into Docker. We've sort of already seen how to do that without Abaco, but then put it in there and run it on Abaco. So there are a couple of things we're going to need to do to prepare the image, the Docker image, before we can run it on Abaco, right? And I've kind of hinted at a couple of these. But the big one is that we're going to have to figure out how to parse this message. Abaco is going to take the input, the message, and inject it as an environment variable. So what we've chosen to do, and this is just a choice, but is to write a separate bash script, abaco.sh, that's going to do that parsing. And basically it's going to take that message variable and just run our run our program with it. And you will see on the next slide, it's really trivial. It's essentially a one-line program, but we decided to make it a separate program so that the standalone Python thing, was still standalone. We could have chosen to put this functionality in classify image.py itself. We could have chosen to make it a Python program. It really doesn't matter, but it was so simple, we just decided to put it in Bash. And then the other thing, though, that we need to do that is make sure that we set up permissions in the image so that a non-root user can run our program inside the container. And if you look back at the Dockerfile I presented at the beginning, you'll notice that everything is kind of set up and owned as root. And our classify image.py file was owned as root, for instance. That's not going to work on Abaco. Abaco does not run the images or the containers as root anywhere. It runs them actually as the UID associated with the TAC account that registered the actor. So, in general, it's actually a good practice anyway, Abaco or not, to make it so that your containers run as non-root users. And so that's what we're doing here. So we've got these. We added a make dir app. We're just going to put everything in /app. And so we add then our classify image.py to that app directory. And then we add abaco.sh, which I'll show on the next slide, in there as well. And then we just run a chmod so that everything in app is available to a non-privileged user. By the way, this code is available, as well as the slides, from my GitHub repo URL here that I linked down there. So if you want to pull this code down or take a look at it in more detail, feel free to grab it from there. So yeah, so here is that bash script. It just changes into the app, and then it runs Python classify image.py, and then -- image file equals our $message environment variable. So this is, I say, the entry point for an Abaco ready version of our app. And then that's really all it is. All there is to it. We can rebuild the image with that same Docker build command. And then another thing that I definitely like to strongly suggest to folks is that they test locally. So run this just as Abaco will by using -e, the -e flag to Docker run to set an environment variable, MSG, just as Abaco will, and just make sure that your container is running locally before you try to run it on Abaco, because if it doesn't work locally, it's going to be that much harder to debug when it's Abaco. Okay, and then finally, you need to push the image to Docker Hub. So today, and one of the features in our roadmap is to kind of augment this, but today, Abaco will look for images on the public Docker Hub. And so any images that you want to run there need to be pushed up there. Okay, so we're going to get roll our sleeves up a little bit here and look at actually hitting the API with a couple of requests. Hopefully this won't be too painful, but I think it's helpful to actually just see some of the basic commands. So here's how we would register the Abaco classifier actor. And I should say that all of this stuff, all the interactions with Abaco require a TAC account and to be set up with OAuth. And unfortunately, we don't really have time to kind of go through all of those details. I do have some notes in the slides on that, and there's links to the documentation on how to get set up with that. So I'm just going to assume that at this point on you've got an access token, which is like something you exchange your TAC username and password to get, and it's good for about 4 hours, and that you've exported it as this variable $ token into the environment. So we're using curl because that's kind of a sort of a common used HTTP client, but really any HTTP client could be used as Abaco is just an HTTP API. But so here's how we would create an actor. So we do a post to the actors collection, passing a reference to the image. Here we're saying image equals JStubbs SGCI classifier. And this is form encoded data. You could also pass JSON data. But that's it. It's just this one HTTP request. And basically what's going to happen is that Abaco is going to respond in JSON. And here's an example response here on the left. Several pieces of data here, several attributes, but the key one is the ID, the actor ID here, which is we're going to need in the second, in the next steps, and the status of submitted. So the actor will start off in submitted status, and Abaco will move it to ready once it has essentially started a worker, which is an Abaco internal thing, for managing that actor's queue, and the worker has been able to pull down the image. So if there was some problem pulling the image, like if the image didn't exist on the Docker Hub or some other problem, then the actor would go into error status instead of ready, and at that point you would need to fix the actor definition before it could process messages. Okay, so remember that actor ID, there it is in yellow again. We're going to be ready to now just execute our actor, right? And so that's done by posting, again, creating sort of this RESTful idea, right? We're going to create a message. We're going to post to the actor's messages collection. And so that's done by making a post request and passing message equals, in this case, because we're just passing text, which is the URL of the image that we want to classify. And then it's actors v2, the actor ID / messages. Okay, Abaco is then going to respond again in JSON, but it's important to note that it actually is going to respond immediately. It's going to respond with an execution ID here in purple, which we're going to be able to use to track the execution. It also returns the message data that we passed it. So it returns immediately. In other words, the execution is asynchronous to this request. You could have posted 10,000 other messages before you posted this one. And basically behind the scenes, what Abaco is going to do is it's going to put each message in a queue. And then the actor is going to run in order of that queue. So once you have the execution ID, you can check on the execution. So we're not creating an execution here, we're just checking on the details. So in REST, that's a GET request. And here you can just see that we're chaining together our actor ID. So the URL is actors v2, our actor ID from the first slide, then the / executions collection off of there, and then the execution ID. So basically Abaco returns immediately in JSON whatever the status is of that execution. It does track that, and it will basically set a status of complete as soon as the container has exited. And once that happens, it will add a bunch of additional metadata about that execution, including this final state stanza here, which includes things like the exit code of the associated process, as well as an error message if there's one. But it also includes things like the runtime, here 9, that's seconds, the I/O that was consumed, the CPUs that were consumed, etc. This is actually an abbreviated, a sort of truncated response. The full response is a bit more involved, but you get the basic idea. It's going to give you information about the execution associated with that execution ID. Okay, so once we get a status of complete, we are ready to retrieve our result. And so, Abaco has a number of ways, actually, a couple of ways at least, of dealing with this. But the simplest way is to just use the logs endpoint off of the execution to retrieve standard out associated with that container. And so that's exactly what we're doing here. We're making a GET request, right? We just want to get the logs associated with our actor ID, which is in yellow, / executions, the execution ID here in purple, and then / logs. And you can see that Abaco just returns text, a text content type of exactly what we got before when we were running it on our local machine. Okay, so that's really the bulk of what I wanted to say as part of the example. I did want to point out that we do have a couple of other clients. You're not forced to use curl to talk to Abaco. We have a CLI, which gives you some convenient, a sort of easier to use commands like Abaco create for creating an actor, or Abaco submit for sending a message, right? And then you pass it the actor ID. We also have a Python SDK. So once you have a client object that has your token in it, you can do things like cl.actors.list to list all of your actors, or cl.actors.add to create an actor, and so forth. So you can interact at least in Bash and in Python in a sort of more native or friendly way in those environments. Okay, so just some concluding remarks about what we could kind of do as next steps. I mean, so there's nothing to stop us from sending our actor, thousands of messages to classify, a bunch of images that we have, sitting on some file server somewhere. We could give our actor something called a meaningful alias. So instead of using the ID, we can actually create an alias that we define that has some meaning. And then once we have that, or even if we didn't do that, we could then share that actor with our colleagues, or even publish it and make it so that anyone could execute it. So there's a permissions model and a permissions endpoint associated with actors that Abaco allows you to use to do that. We could expose this actor in a web application. We could embed it in a science gateway, right? I mean, that's kind of one of the big use cases. So you could have some web form in your gateway that says, give me a URL, and that gateway just turns right around and makes an HTTP request to Abaco to run the classifier. But there are, like I say, a number of additional features. I just encourage anyone who's interested to check out the documentation, which is there on Read the Docs. And that's it. So if you have any questions, I'm happy to take those. Abaco is on GitHub, the source code itself. So in addition to the docs, feel free to check that out. We have our issue tracker is there, as well as sort of kind of our roadmap, our public roadmap. And then also just a quick plug for the Tech Cloud Slack team. So if you're interested in Abaco or really any TAC Cloud APIs, feel free to reach out to us and join that Slack team. We have an account on there, CIC support, that you can just on any of the Slack channels for support. It's monitored 5 days a week, 9 to 5, and so yeah, feel free to do that or to send us email at CIC support at tech.utexas.edu. But yeah, I think that's all I have.
Well, thanks, Joe. That was really efficient, given you said that you had so much to cover. And Sean wrote back and he said thank you. He thought this was excellent. So I'll give folks a moment to think about any questions. Aha, here's one. So Mark writes, you mentioned Jupyter earlier. Can you expose ports and run Jupyter notebooks through Abaco?
Yeah, that's a good question. So Abaco does not provide a mechanism for exposing ports today. Everything needs to be done through the API. So if you were wanting to talk to a service, that was an Abaco function, you would have to send it a message. But what we do have, and this is, I'm glad someone asked about this, because this is, I think, one of the coolest things. It's pretty nerdy, but this is the kind of thing I really like. So what we do have is a way to basically take a Jupyter notebook and run a cell, run an executable cell from that notebook remotely on Abaco. And the way it basically works is pretty simple, but let's say I want to run f of x. I have some function f. in my notebook and I want to run f of x in my cell, basically what it does is it sends a message, which is a binary message that contains a Python serialized. Sorry, this only works for Python too. I should clarify. We could add other languages, but right now today we only have support for Python. But if f is a Python function, then what this basically does is it serializes f using something called pickling, and it passes that serialization through as a message. And then on the other end, Abaco deserializes that f and invokes it. And then in the same way we can stream back, an arbitrary Python object as the result using the same serialization and deserialization techniques. So what this is good for is if you have a Jupyter notebook, but you want to run some function on the Abaco cloud because maybe that has access to Corral or some high performance storage, or maybe it has more CPUs available to it or what have you. Then it's a good technique for that. There is latency obviously in packaging up the function and sending it and sending the result back. So you have to take that into account, but it can be a really good solution for scaling certain Jupyter, certain use cases in Jupyter.
Thanks. I'll just mention for the benefit of those of you who may be relying on me to pass on messages, so my colleague Nighty, who's on this monitoring this, in the middle of a really giant thunderstorm here with dramatic lightning. So if I get disconnected, somebody else hopefully can fill in. But another question just came through from Chunhan. He asks, Abaco can run computing jobs on Stampede?
In theory, it could. We don't run any jobs right now on Stampede. We do have some high performance. Well, I don't know. Depending on your definition of high performance hardware, we do have some high performance hardware in the Abaco compute cluster. The challenge with Stampede in particular is that it is just such an overly subscribed system that basically taking a bunch of nodes or even a couple of nodes from Stampede and just setting them aside for Abaco functions hasn't been a viable or really just a good use of resources. But we've used our Hikari system, which is it's a much smaller system than Stampede, but it looks a lot like it. It has the global file system mounted. It has high-speed interconnect. So what we can do is basically put arbitrary nodes into the Abaco compute cluster. We put some GPUs in there as well, and then Abaco does have a way of routing certain actor executions to certain physical resources, and that's how we do accomplish things like saying oh well, this actor needs this kind of compute resource, and so so we can do that, but we don't run anything on Stampede in particular.
Okie doke, thanks. Another question has come in from Barry, who asks, related to HPC utilization, any plans for enabling support for singularity?
I'm not sure I completely understand the question. If it's about, are we, have we looked at enabling Abaco actors to be defined as singularity images? The answer is yes. And this is a great question. I mean,
he says yes, so I guess that is the question.
Okay, cool. Yeah, I think that would actually be relatively straightforward actually to do. The main thing is we need to have a way of referencing those singularity images. This is the main blocker, right? So we have Singularity Hub. That's the sort of official Singularity offering, which is publicly available, blah blah blah. But it has a fair amount of limitations. Like we actually they were worried we were DDoSing them one time because we were running a training where everyone in the training session pulled a Singularity image, and and so it was like 30 people who hit this, or whatever it was, 60 people who hit this, hit Singularity Hub at the same time for the same little test image. And they were like, please don't do that. And so it was like, okay, well, that's fine. We won't do that, but it also means, we probably shouldn't use it for this, because, we need to have a way of basically doing a lot of high volume access of the image registry. So we've looked at Singularity Registry or Singularity Hub. We've also looked at auto converting. So you can take a Docker image and just convert it to a Singularity image. And in fact, we do that for some of our other projects. It works, and so that's another option. Is you still pass a Docker image to Abaco. You say, hey, use this, but maybe you set some flag that says run as a Singularity thing, and then we do a conversion process. And that would absolutely allow us to, as the questioner suggested, that would allow us to run on a lot more HPC resources. So, I think it's definitely something that's being considered in our roadmap.
I would very much like to thank you, Joe, for presenting a terrific webinar. If you could see all of the just chat messages that have come through BlueJeans in the last few minutes, there's lots of thank yous. So I think we have a grateful audience here for that really concise and coherent explanation of all this technology, which is really useful. So with that, thank you everyone for joining us. Yeah.
Yeah, thanks for the opportunity, and thanks everyone for joining. It was a lot of fun. So